Meyer soon will make a presentation about numerical methods and models, but the focus of my presentation is the possibility of comparison the results which we can take from our simulation and microstructural investigation of the metals. I will discuss about basic level and its existence at SPALL fracture of metals. Okay. That's my outline. I briefly discuss about plasticity, our plasticity model. Then I will say about our microstructural investigation and present the SPALL fracture model. Our model of plasticity and fracture consists from several parts. The central parts, it's mechanics of continuous media, then a big part of plasticity models with different mechanisms of plasticity such as dislocation, slip, grain boundary sliding, twinning, and maybe so on. And of course we include in our model a model of fracture, dynamic fracture. I will not show this part of our models. You can find it in our publication, and we'll discuss about fracture models. Equation of continuum is in its standard form. It's continuity equation, equation of motions, where we divide full stresses on pressure and deviatory part. And then is the main place in our equation. It's we include in deviatory part the tensors of plastic deformations and tensors of fracture. And we use sum of equation of state. I will discuss about the problem when the thin metal plates collision with the metal targets. Our model in this one-dimensional cases give shock waves propagation through the targets and volume fractures of defects behind the shock waves. And then we have distributions of different types of defects, such as dislocation density and, for example, twins, volume fractions through our target. But also, if the deformation conditions allow it, we have a SPALL fracture, and at this case we have a SPALL fracture region and two waves that move from both sides of our SPALL. And also we can predict a distribution of different defects and compare it with, for example, microstructural investigations. But focus on SPALL fracture when thin metal plates collision with the targets. If we will increase our impacted velocity, we will have a crack, and at a further increasing of velocity, we will have a big crack and then SPALL plates. Experimental experiments will perform in St. Petersburg by Yuri Meshcheryakov and its groups And we have performed a microstructural investigation of this SPALL fracture. It's well known that SPALL fracture is multi-scale process, and there are some different scale levels. It's a macro scale level. This is two spallation plates at different impact velocities. Then we can see fracture elements with sizes about some hundreds of micrometers, and further we see that at this on the top of these elements we can see elements with sizes about some tens of micrometers. And then we see the pores which collision which is other with sizes about some micrometers, and the next level is the sub-micrometer pores. And the question which we ask at which of these scale levels is the main, which determines the fracture process at all, and determines the formation of new surface at SPALL fracture. So, then we make constitutive models with models of fracture, where we about these models Alexander Meyer will have a next talk, but I say briefly that we include our fracture in fracture tensors. Then we can describe growth of our microcracks. Also, our microcracks or pores, they grow by the dislocation moving, and we include really our plasticity model in our fracture model in these terms. And also we consider some kinetic model of microfracture. It's a nucleation of new pores, and we think that there are two regimes of this nucleation. It's a nucleation of really new pores and an activation of existing pores. This is a comparison of our model with some experimental data and data of molecular dynamic simulations. That's clearly seen two regimes at medium strain rates, where the pre-existing voids begin to grow, and at very high strain rates, where the new pores nucleates, and it's the main mechanism maybe of fracture. And we can take from our model tensile stress to strain rate curve. Also, we can have from our model a free surface velocity with some reverberations, and you see as SPALL fracture that our model is described. Yes, but also this from this side we have a collision, and this is velocity field, and the top it's mean radius of the formation pore. That's a SPALL crack, and at the bottom it's a volume fraction of its pores. And then it's I think main slide of presentation. It's a calculation result of void diameter at which they coalescence with each other to strain rate. And this is our experimental distribution of fraction of pores with different sizes, which we take from our microstructural consideration. And you can see that for aluminum D16 alloys at this strain rates, we have a good agreement with our microstructural simulation. And then we can conclude that the first structural model can describe both as microscopical mechanical response on the material and evolution of the material microstructure. There is some base scale level that we can predict by our models, and this scale level for aluminum D16 and these strain rates is about 1 to 5 micrometers. Thank you for your attention.